Hello, dear GMAT41's channel members, subscribers, and viewers. You are welcome to the GMAT41's YouTube channel. In our physics class today, we are going to give attention to the progressive wave equation and, of course, how to use that equation to solve certain problems related to wave as connected to the terms that are used in describing wave motion. You would recall that in our previous physics class, we discussed the terms that are used to describe wave motion to include amplitude, wavelength, frequency. We talked about the concept of period. We also explained what phase and cycle is. I told you that there is this progressive wave equation that can be derived by making use of those basic terms in the study of wave motion. So in this class, we are going to be looking at that progressive wave equation, and I hope that you have already covered that previous video lesson on terms used in describing wave motion. Alright, before we kick off this class, I would want to appreciate our new subscribers. Alright, thank you very much and welcome to this wonderful channel. You can always be assured that the GMAT41 appreciates your presence. Thank you very much. If you just tuned on into this channel and you are yet to subscribe, please do subscribe, turn on the notification bell, personalize the subscription so that once I upload any new content, you will be personally notified. Don't forget to like and share our video lessons also so that other scholars will have access to it and benefit. Always remember you can become a channel member to support GMAT41 and gain even more exclusive benefits, especially for channel members. Alright, let us get to business. The progressive wave equation is what we are going to treat. And then as we move on into this, I would like to once again display our progressive wave graph. It was shown in the previous lesson, and I would also want you to take a look at it as it displays on the screen. Alright, so this is the progressive wave graph, okay? And of course, you remember that we described this graph using certain terms that are used in the study of progressive wave motion. Now, if you look at this graph, you would agree with me that it is a sinusoidal graph. What does it mean? You know, wave motion is a periodic motion, and the graph is patterned, follows the sine graph. You know, in mathematics, under trigonometry, we have the graph of sine, we have the graph of cosine, we have the graph of tangent. When dealing with wave motion, the graph follows that of sine. It could also follow the cosine graph as well too. The only difference between sine graph and cosine graph is that you can see the sine graph moves, just upward. If you want to start from the origin, fine, just like you have in the graph displayed, it moves from the origin upward and then it continues moving in that order. But for cosine graph, okay, let's say from the origin, it tips downward first. Are you getting me right? Curves downward and then it continues its motion like that. So both the sinusoidal graph and cosine graph can be used to describe wave motion, alright? But we prefer to follow that of sine. And that is what you have here showing on the screen. Okay, so in line with this graph, we would like to recall, okay, it's a kind of reminding ourselves of the sine equation. This we meet in trigonometry mathematics. And what is the sine equation? The sine equation is given as y equal to a sine theta. Where in this case, in the study of motion, this theta, like I explained in our previous class, is the phase angle. The phase angle, alright, which defines the state of vibration of a progressive wave as to whether the wave is at its maximum state of vibration or minimum state of vibration or the mean, the rest state. That is what this theta is. And then I remember that I told you the formula of this phase angle. Okay, so if you have not taken the previous lesson, I urge you please to watch it. You can go through the GMAS 41's physics playlist and you would see the previous video lesson on terms used in describing wave. However, towards the end of this particular class, I am going to show, the thumbnail video that would lead you to that previous class. You can simply tap it and then it will take you directly to our previous lesson on terms used in describing wave motion. So make sure you stick around, watch this video lesson down to the end so that you can get to see that previous lesson. Now let us move on. So this theta or phase angle has a formula related to angular frequency and the time it takes the wave as the wave is traveling. Alright, in circular motion, we obtain that theta is equal to omega t. So this formula was established in our previous class. And in that case, we are going to have the wave equation to now be y equal to a sine theta. Alright, that theta is going to be replaced now with angular velocity times time, omega t. Alright, we went ahead to establish in our previous class also that the angular frequency, angular velocity, is equal to 2 pi f, where the f is the frequency. So I can still work on this formula to get a sine. Then in place of this angular frequency, I'm going to substitute 2 pi f, where the f is the frequency of the wave, and then that's going to be multiplied by the time. Remember, our a is amplitude, the maximum displacement of the wave from its rest position. So we've been able to establish the progressive wave equation up to this point, but we are not done. We are just starting the business. Is that okay? But it's a simple derivation. Don't worry, follow along. We have established all the things we need previously in order to understand this wave equation that we are going to establish in today's class. Alright, I hope you understand up to this point, right? Do you have any question? If you don't have any question, remember you can ask and I will pay attention to you. Just make use of the comment box below this video lesson and ask your question. I'll be there to respond. Now let us move on. Our frequency, we know, is equal to the speed of the wave divided by the wavelength of the wave. That is v over lambda. Once again, our previous class explains that, which means that the y is going to be a times sine 2 pi. In place of this frequency, I'm going to substitute the wave speed v divided by the wavelength lambda. I'm going to multiply this by t. Okay? And then we know that Vt, that is the speed of the wave times the time, is equal to what? Speed times time will give you what? Yeah, let me hear you. Don't worry, speak. I can hear you as long as you took the previous video lesson, okay? If you actually attended that class, yeah, taking it, you would know what Vt means. So tell me, speed or velocity times time is equal to what? That's very correct. It's equal to distance covered by the wave. Alright, so this is going to give us y equal to a sine 2 pi. Then in place of Vt, we are going to replace it by the distance covered by the wave as it is traveling. And the distance, we are using x for it. So this is going to be x divided by what? By the wavelength, lambda. Alright, I'm going to take this as equation 1. Okay, so this equation 1 is the standard equation of progressive wave, taking into consideration the total distance, x. Now we have established this progressive wave equation in terms of distance. Progressive wave equation in terms of what? Distance only. The distance that the wave covers as the wave is traveling. But do you know something? As a wave is traveling, it's moving with speed. And as it's moving with speed, a certain time is being what? Covered. Which means if a wave is in motion, we can use the speed of the wave and the time of the wave at any particular time to determine the distance that the wave covers at any particular point in time. So what we're going to do here now is to try to introduce time into this equation. Although we have time here, I want us to see an equation of progressive wave that will contain the distance x and the time. So that is what we are going to do at this point. And for us to achieve that, I would like us to quickly look at this, okay? Let us consider this on the board quickly. I'm going to do the analysis. Now, imagine that we have our graph, okay? We have our graph. Now, let's say this is x. Then I have my wave move this way, and then something like this. So let's assume that the wave is at this point, okay? Now there is a certain distance left to cover. We know that from this point to this point, there is a certain distance covered so far. Is that okay? There's a certain distance covered so far, we know that. At this particular point, let us define the speed of the wave here to be v. Let's define the speed of the wave at this point to be what? V. And then it corresponds to a given time, t. I hope you're following, right? So I can actually get the distance the wave covered from this point to this point using the speed of the wave and the time it took the wave to get to this particular point. And to do that, we could just simply write that from this point and then down to this point, we're going to have that the distance covered is equal to Vt. Let me call that distance x1. So the wave has covered the distance x1 from this point to this point. With respect to the speed of the wave and the time, that distance is what? Vt. What about the remaining distance? What is going to be the distance from here to this point? The remaining distance. If the total distance is x, out of which it covered x1, which we obtained to be Vt, we can get the value from this point to this point. And how can we get the distance? The total distance is x, out of which you have obtained x1, which is Vt. So the remaining distance is going to be total distance x minus Vt, where Vt is x1. You have the total distance x, out of which you've gotten the value from here to this point. So the remaining distance is going to be the total distance, remove the one that has been covered. So what is left would now be the remaining distance that the wave has to travel to complete that total distance. So what have we been able to establish here? Respecting the remaining distance, we have the formula to be total distance minus what? Vt. So what we're going to do here is come back to this equation 1. In place of this distance, we are going to replace the leftover distance, which is x minus what? Vt. Are you following? It's a kind of substituting, all right, for this distance. We're going to respect the leftover distance to be covered, which is x minus what? Vt. So let us do that and see, please. If x is equal to x minus Vt, I explained that there already. The implication is that our progressive wave equation y is going to be a sine 2 pi. Then in place of x, I will fix x minus Vt. Of course, you know that originally this 2 pi x is divided by what? Lambda. So this is going to be divided by lambda, the wave length. This is interesting. I'm going to call this equation 2. Now, permit me to asterisk this, because this is a fundamental progressive wave equation you should know. Your examiner can push you to this direction, are you getting me right? And use this to ask you certain questions as necessary. I hope you get up to this point, right? Remember, you've got a question, please make use of the comment box, drop a question, and I'll be right there to respond to it. We're going to still work on this formula. Let us open up the bracket here. If you open up this bracket, this 2 pi over lambda, that is wavelength, is going to multiply this x, is going to also multiply this Vt. So we're going to get, good. So this is what we are going to get when this 2 pi over lambda wavelength multiplies x, and when it multiplies Vt. Now, I am interested in V over lambda. V over lambda. V over lambda is equal to frequency. The frequency of a wave is defined as the speed of the wave divided by the wavelength. There is this relationship between them. I established that in our previous class. So in place of that V over lambda, I'm going to fix frequency so that the progressive wave equation takes this form. Right, 2 pi x divided by wavelength, and then this is going to be 2 pi. In place of speed over wavelength, I'm going to fix frequency of the wave. Now you notice that I have replaced V over this lambda wavelength by the frequency of the wave. So the equation takes this format, and this form of the equation is also very important. Examiners also like using this, progressive wave equation form to ask exam questions also. So you want to take note of that. I have asterisk equation 2, I have asterisk equation 3. These are the major progressive wave equations a student should memorize. They should have that at heart. Because most times, like I said, examiners, they usually love, referring to those equations. Can we move a bit further? Now, this 2 pi divided by lambda wavelength has a name given to that quantity. We use K to represent it, 2 pi over lambda. That is called the wave number. That is called what? The wave number. Take note of that. K is equal to the wave number. Then, like I established in our previous class, 2 pi f, I also even showed it here, is equal to angular frequency, 2 pi f. So, we are going to have that angular frequency W, also known as angular velocity, is 2 pi f, which means that this 2 pi f, we can use angular velocity to represent it. And therefore, our progressive wave equation will take a much more condensed form as amplitude times sine, open bracket, 2 pi over wavelength is equal to wave number k. Is that okay? Then multiply by x minus 2 pi f is the wave angular frequency or angular velocity. That's going to be omega t. Good. Now we're going to take this as equation 4 asterisk. And we have arrived. You love this equation derivation, right? We've been able to establish the progressive wave equation. In this form, equation 2 asterisk, we have been able to establish it in the form of equation 3 asterisk, and of course you saw that of equation 4 asterisk, where we introduced the concept of wave number and the concept of angular frequency once again. These are the progressive wave equations that a scholar is expected to always bear in mind. Because like I said, when questions are given, problems are given for you to solve, usually they are linked to either equation 2 asterisk, 3 asterisk, or 4 asterisk. But all in all, you need to understand what has been done here. Is that okay? This equation is what we refer to as the progressive wave equation. Either this, or this, or this. But remember, all of them were obtained from the standard form, equation 1. Is there a question? I hope you understand this derivation of progressive wave equation. Alright. We are going to see how we make use of this equation to solve problems on progressive wave. Don't forget, this K, I refer to it as wave number. I think I'll have to quickly define it and tell you the formula, and tell you the unit rather. The wave number of a wave is defined as the number of cycles covered per distance. The number of cycles covered per what? Distance traveled by the wave. You know that our lambda, wavelength is distance actually. And from our previous class, I explained wavelengths to be the distance between two successive crests or two successive what? Trough. So the number of cycles covered per a wavelength is what gives us what? The wave number. Does that make sense? 2 pi here represents number of cycles. You want to take note of that. We have this relationship. One cycle is equal to 1 revolution, is equal to 1 oscillation, is also equal to 2 pi in the unit of radian. Is equal to what? 2 pi in the unit of radian. And it is also equal to 360 degrees. That is the unit of degrees as angle. That's 2 pi. So you want to take note of that. That's why I refer to 2 pi here, the definition of wave number, as the number of cycles covered over a given what? Distance, wavelength. That distance is specific. I remember also mentioning in our previous class that every one wavelength is a cycle. And 2 pi here is a cycle, I said. So you see, covering a wavelength, you have made 1 cycle. So you have number of cycles, once again, per the distance covered by the wave. Now this 2 pi has the unit radian. and wavelength has the unit meter. Therefore, what do you think is going to be the unit of our wave number K? That's good. The wave number is going to have the unit rad per meter. That is radian per watt per meter. So take note of that concept, very important. Alright, let us now see how we can solve problems using the progressive wave equation. If you're yet to subscribe, please kindly do so, okay? Like I said, you can also become a channel member, please. Support GMAT41, okay? If you tap the join button or tab just below this video lesson, okay? Tap the join tab, and then you would see the packages available on the GMAT41's channel. Select whichever that is convenient for you. Support GMAT41, please, and then you become channel member for more exclusive benefit. Please let us move on and take our first question, applying this progressive wave equation.